branches that have a life cycle of 2 to 4 years, that it's important to investigate. Let's see, I've been here a long time, 27 years, something like that. And I basically know where all the bodies are buried. That's why they make me a tour. So what we're going to do this morning is we're going to watch a short propaganda film that every laboratory produces, arming our into the future, and that kind of thing. And then we're going to have a little question and answer period if you'd like to ask questions. There's also some amount of explanation that's going to be necessary because the video leaves some things hanging to some extent. And then we're going to go on a tour. We're going to go briefly through the lobby, and we're going to talk about ITER, the International Thermonuclear Reactor. We'll talk briefly about NSTX. We can't go to NSTX because it's under construction. We will go to the control room, and we will take a virtual tour of NSTX. We'll do a flyover. And we also have a series of PowerPoint slides that show pictures of the last day of operation, and then periodically through the entire construction process. And the last picture should be this morning's, where we are. So you can see how the test cell is evolving. And you can see how tight it is. And then we're going to leave there, come back up here, and we're going to go over to the CS High Bay area, which is where they are currently building the center stack for NSTX, and we'll talk about what that means and what it looks like. They have just completed one of the critical steps, which is doing vacuum pressure impregnation of a first quadrant of the center stack. And we'll see how that, they're pulled it out of the oven, they've taken the cover off, and we should be able to get in there and look around. There are no restrictions on taking pictures. You could take pictures to your heart's content. You can ask questions, and the best I will try to answer them, but if I don't know, I'm going to say I don't know. There are certain things that are above my pay grade, and, and when you ask me things like, when do you think fusion will be here? My answer is stock, and that is, depends on how much money you want to spend.
Yes. Yeah. Yep. Right answer.
As it is, the progress has been good, and worldwide, people are making more and more progress. Other countries are proposing new machines, demonstration machines, where they have big Q over 1 kind of thing, heat out over heat in, or energy out over energy in. A standard power plant has a big Q of about 25. So a power plant puts out 25 times as much energy as it takes to power it. Even nuclear coal, it's 20 to 25. Right now, we're trying to get past Q of 1. And that's a very big barrier for us. And we'll talk about some of the technological challenges that poses. All right, do you have any questions before we show the short little video?
What's the potential for the big Q for commercial fusion?
The potential? Well, you have to build an entire industry to do it.
Yeah.
There is really no infrastructure in the country for building parts for fusion energy devices.
Wow.
There isn't even an agreed upon design for what it would look like. And there are certainly competitors to magnetic fusion energy confinement, including inertial confinement. But we think that the magnetic has a bit of an edge because it's been developed longer than the inertial confinement fusion. And its progress has been rather remarkable in terms of its confinement and so forth. It actually beats Moore's law in terms of memory device shrinkage. So it is moving very, very much forward. That little picture was the first plasma of NSTX. And that clip was cut from an old version, and they used to explain what that is, and they decided not to explain this time. what that is first plasma on an STX. And the reason that that is such a big deal is when you propose a major science experiment to the US government, you tell them, I can build this machine for, pick a number, $93 million. And they say, they look at it and they want more detail, and you give them more detail. And then they say, okay, go build. Here's $93 million. But that's all the money you're going to get to construct that thing. If you've made a mistake or you hit a technological problem that you have to spend more money on, tough. You've got $93 million. So what happens is you're what we call you're in the construction phase. You're building the machine, you're building its infrastructure, you're hooking it all up, trying to make it work. Now, the first time that it works, it's no longer a construction project. So whenever that time is actually very important. It says the total project cost is when you make that first plasma, at the total contract construction cost. What happens is, when you make that first plasma, you're now an operating machine. And a whole bucket of money, different bucket of money, opens up. Because now you're in another budget. You have a different budget for operating. So that's why everybody is cheering. The director is there, everybody.
Keep our jobs.
Well, you have to realize, when you're at the end of a construction project, everybody is looking at every dime because you're probably eating the last little bits of that construction project. And you want that total contract, the total project cost to be as low as possible, not to mention on time. Anyway, NSTX came in on time, came in on budget.
When was that? When was it?
10 years ago.
Really?
10 years ago. 2003, 2002, actually, could be 11 years now. Yeah, TFTR shut down in 1997. We started building, it could have been 2004. I've been here so long. So, do you have any questions about the video that you saw?
Could you say something about the difference between the donut design and spherical design?
Sure, and actually we'll talk about that when we go out to the lobby. So, great straight man, thank you very much.
NSTX stands for what?
National Spherical Torus Experiment.
Yeah, one of the speakers said that most of the universe is comprised of plasma. Is it true that fire is a plasma?
Yes.
I'm sorry. Well then, the ancient Greek philosopher Heraclitus had it right then, didn't he? Intuitively.
Well, what he said was 99% of the visible universe. So he had a little qualifier in there, because if you look at modern cosmology, you could probably answer this better than I can. Modern cosmology, they have dark energy and dark matter, and so the total energy content is going up, and most of it is hidden from us. So,
How many spherical torus experiments are there?
well, there is, I don't know all of them, but I can tell you that there's, we have, NSTX is probably the largest one in the United States, though there are smaller machines.
Probably in the world.
Probably, well, MAST is a little bigger.
Your website says when it is rebuilt, it will be the largest of its type in the world.
And what that means is it'll have more capability than most of the machines in the world. It's basically being upgraded to push that technology to the next level. So there's this one, National Spherical Torus Experiment. There are some universities that have small machines. The University of Wisconsin, for example, has a small Stellarator machine. There is a machine called MAST, which is in England, which is managed by Cullum, I think, by Cullum. Other spherical torus. There's one in Japan. But those are the only ones I can come up with right now. Yeah.
At one point it said that the TFTR had produced enough power to power a small city,
Yes.
but that depends on translating that heat
Yeah, so
into...
let me translate that, okay? So yes, it did produce 10 million watts of energy for briefly, and you can see the nice plot that shows you reaching the 10 million watts. But what you really need to know, that they don't tell you in those kinds of films, is, remember that big Q thing?
Yeah.
So the big Q for TFTR was at a maximum of 0.3. So what that said was if it made 10 million watts, it took 30 million watts
Right.
to make that 10 million
It
watts.
can power a small city as long as it takes the power from 3 others.
And you need to realize that that doesn't include efficiencies.
Right.
Inefficiencies. So the power conversion equipment soaks up a heck of a lot of energy. They're only probably 50% efficient. So you're probably down to 6 times. No. Let's go 30%.
0.15, cube 0.15. Engineering cube 0.15.
And it's very, very little, basically, compared to how much power we suck off the PSE engine.
You, with the is it deuterium, tritium?
Yes.
Okay. And so the energy comes off as neutrons.
And gamma rays, yes.
Okay. How is that then, would that be translated into, do you use liquid lithium on the surface of this one, or what do
Well,
you?
we'll
what do
talk
you-
about that.
Okay.
That's one of the key technological things we are working on. We'll talk about that when we actually get a chance out there where it's warmer.
What would the power on ITER be?
ITER is supposed to reach a Q of 5.
The amount of how many watts would it be?
Well, let me put it to you this way. It's not advertised, but they're building a nuclear power plant nearby to power. Does that tell you something?
Right, but ITER is still, I mean, it's not supposed to generate electric power. I mean, it's just it's a fusion experiment that wants to show that we can create a tokamak that has 10 more times the energy output in the neutronic energy output than what it requires to run, right? And then afterwards, the next step would be to actually be able to get that energy and turn it into electric energy, right?
Yeah.
So it's a point that you want to turn it on and then have it when you want to actually make a power plant. You want the Q to effectively be infinity, right? You want it to keep on running just by itself, right? So you turn it on and then just the fusion itself, like the sun, the fusion itself is going to be the one that's going to help it run it.
I have a question on, there's discussion about potentially using helium-3
Yes?
for fuel, which my understanding is releases a proton instead of a neutron,
Yes.
which somehow makes it easier to contain or whatever.
You get less elemental transmutation in the surrounding materials. Yes. And so you end up.
Because of embrittlement?
Well, it just happens from when you got neutron bombardment. You literally have, nuclei are basically changing. So you're changing cobalt into, cobalt 60, and which has and strontium 90 and things like that, which have thousands of years of half-life. Yes, that's true, but in general, even that kind of process produces much, much less residual radiation than, for example, a fission power plant. You don't have any of the daughter products.
Right, the thing is that neutrons can't be contained inside the thing, so they just go everywhere. Whereas all the byproducts of a helium-3 reaction are electrically charged, so they're all stuck in the magnetic configuration.
And isn't there more direct conversion to electricity possible with charged particles?
That hasn't been explored as far as I know.
That's something that I've questioned myself. I'm not exactly sure how it is that they intend to do it, because I understand the way to get it from neutrons, but I'm not exactly sure how to get it from a helium-3 reaction.
There was a guy named George Miley who wrote a book on energy conversion, and I read it probably 10 years ago. He talked about actually using compression techniques where you're literally looking at the plasma like you would a Carnot cycle. So you heat it, you compress it, and as you compress it, the reaction rate goes up by 400 times, and then you literally let it free expand, and while it's free expanding, it's literally driving current through the coils, and you're turning the magnets around, so now instead of sucking in energy, they're pushing energy out. They develop a voltage going outward. Anyway, that was many years ago.
I mean, the big problem with helium-3 is where to get helium-3.
Yes.
Very where it's deteriorating.
Moon.
Yeah.
But then you have to build an infrastructure to get there. A real key point about that when we talk about Stellarator and tokamaks and TFTR and now NSTX when we get out there. Any more questions?
What's the significance of the term stellarator? I think of a stellated platonic solid or something.
Actually, Stellarator was a word invented by our godfather, Lyman Spitzer, back in the day. It's actually a Princeton invention, which is why I think we always...
It's like a star maker. That's the idea, right?
That was the idea.
Stellarator.
And we'll talk about that when we talk about NSTX. So let's hop on out. Here we have about ITER, the International Thermonuclear Reactor. It's being built in just outside of Cadarache, France. It was built on a green field. All the trees that were cut down had to be replanted to someplace else in France because that's part of their rules. It's under construction right now. The facility's under construction. It's about 45 minutes from Marseille, I believe, from Marseille. And it's basically, as you heard, probably the largest collaboration in scientific adventure, representing over half the world's population, which I think is just very cool.
Wow. Yeah.
So the United States has a reasonably small role in this. The construction is being spread out over many of the participants. Some of the things we're doing, one of our engineers is responsible for the steady state electric power network. This is the thing that brings the power in and distributes to, it's the AC power that needs to be brought in, controlled, and then made available to the rectifiers, which turn it from AC into DC.
Do you store it? Do you store it like for a shot?
I don't think so, and I'll tell you why in just a second. And so you can see the artist's rendering is pretty small. The other thing is one of the strengths of Princeton is actually diagnosing high temperature plasmas, and so we are actually contributing to some of the where is it? Diagnostics. There we go. Where you'll see these port plugs here. The United States is building some very important port plugs for diagnosing the plasma. Now, these port plugs have to be particularly designed because they need to be robust to the neutron flux and gamma flux coming out. So there's a lot of zigzags, little labyrinths in there, so there's no direct path for neutrons to come flying out. You also need to realize that this horizontal port plug, it weighs about 42 tons. So,
Wow.
and this one weighs about 23 tons. So you don't just kind of like go in and it's not like a cassette. It's not like a cassette. So we're proposing to the ITER project of using the old TFTR test cell, which is now empty, as a port plug test facility. And what that would be is countries would send their port plugs, and the ones we produce in the United States would come to us, be handled in our test cell, and we would actually test them at temperature. We can't test them in a neutron environment, but we can take them up to temperature. We can put them in a vacuum and basically make them ready so that they can be shipped out here directly to ITER and be installed and hooked up. We would finish all the interfaces and so forth. We think that we have the right infrastructure to handle that kind of stuff. We have the methodology laid out, and we even had a test cell layout. They're thinking about that.
Where are they actually built? Here or?
So these port plugs, they'll be built, some of them will be built in Oak Ridge, I presume. I think it's going to be a collaboration. Now, the American headquarters of ITER is in Oak Ridge, Tennessee. And there are a lot of people who are working on the ITER project and coordinating all that stuff.
I'm sorry.
So, say.
What's the contribution from the United States in terms of approximate budgetary
Right now, it's about 45 million
to the ITER?
to ITER. And let me also say that contrary to the Department of Energy's promises when they signed the contract, that 45 million came directly out of the domestic program.
Oh.
And it's scaling up, right? For these years, every year it's gonna come up. And since they're effectively saying the sum between the domestic budget and the ITER budget stays the same, so everything comes out of the domestic.
That's why the MIT Alcator is being
Yes.
shut, and you guys are being cut,
Yes.
yes.
Great.
Yes. So you understand the situation very well.
Very familiar with that.
Okay. So you see, you asked about whether we stored energy for the pulse, and I don't believe that's true. A lot of these coils, both the center stack coils here, these are magnets, very large magnets. This center stack has superconducting coils in them, niobium tin superconducting, which means it's cheaper to cool them down to their critical temperature, start a current flowing, and just leave them turned on. And so, because you can't shut that current off very quickly, it's even hard to change it because of the inductance in that coil. But you're talking about having millions of degrees centimeters away from 4.2 degrees Kelvin. You know, pretty tough, Some very large engineering problems to be solved. And to give you an idea, this is our typical 6-foot man here, right? So this thing is a very big undertaking. The latest estimates for this were $18 billion,
It fluctuates, but it is in the,
and it's going up.
it is in there.
So I think they
So
started.
that's over the lifetime of the project.
That's over the lifetime of the project, yep. It's supposed to run
The
for.
infrastructure in Calibrate, they had to like rebuild all the roads to Marseille so they could actually truck in the coils.
Because they'll be coming by barge from other countries, because they're so big, they can't be airlifted.
Yeah,
When
and
should-
some they had to actually build that.
When should this come online?
That's also very, very flexible. I think that,
The current estimate is that they'll start running in 18. In 18 they should have.
yeah, maybe
first
that's where I
plasma.
heard the 18, maybe it's not 18 billion, but
No, in 2018.
2018, right. Anyway, it's a big, expensive thing, and it's this large collaboration. So the United States is contributing 45 million this year. Their actual contribution should be about 100 million. The United States is probably the closest to a deadbeat country of all of the participants in participation.
Yeah.
Meanwhile, how much is spent on solar research?
Well, at least 500 million on a
Yeah.
company
Yeah,
that went
right.
up there.
Billions. And when,
So you can figure that out. Anyway, so the national magnetic fusion energy budget is about $450 million a year,
Did that much?
right? So we figure that's a couple of F-18s off an aircraft.
What's inertial, is inertial treated as a separate budget?
It is. There's money coming from both DOE and DOD, but I think they get most of it from DOD.
Yeah. Any idea what that means?
No,
I don't. For example, the National Ignition Facility in California is actually funded mostly by DOD.
Right.
Because they want to use it instead of doing nuclear tests to basically do models for effectiveness and designs,
Right.
things like that.
They have a proposed actual power model for how they would run inertial confinement as a power generator. It's called Life, and what it needs is to be exploding pellets at like 3 hertz or something, like 3 times a second.
Right.
And it's with how difficult it is right now to do those explosions, a lot of people will say that it's very, very optimistic at this point. So it's mainly used as a DoD project.
Okay. Any more questions about this? We'll go over to NSD. So I'm going to answer a question that was asked earlier. What is the difference between a tokamak and a stellarator? In a tokamak, there's actually a significant current running through the plasma. Okay? And that current is producing a magnetic field that, combined with the other magnetic fields, helps to confine the plasma. The problem with that is that it's unstable. It's naturally unstable. If the current center moves around, it means the magnetic fields that are holding that plasma also move and change. And as they change, they affect the current, which can change even more. And that feedback mechanism is Magneto Hydrodynamic Instability, MHD. And it's actually, we have a whole very large contingent of theoretical physicists trying to figure out how to deal with that. It's a very reasonably complex problem. In a stellarator, there's very little plasma current. All of the magnetic field is from the outside. And what you can imagine with that is you can just heat something, you heat a plasma up, and it will sit there and cook. And that's, for a lot of people, the holy grail, because now you can run a fusion reactor consistently. It just bring it up, set the conditions, and let it cook.
And also, as Ray says, that in order to run that current right through the middle in a tokamak, you actually do it by effectively like a transformer. You need to ramp up a magnetic field around it so that it actually induces a current in the middle. But to do that, you need a current that rises, that changes in time. So that's why we're going to show you guys the center stack, which does that. But to do that, we need to be increasing the current, but there's only so far we can actually increase it. So there's a certain time limit that you have.
Okay.
Is the ether considered a spherical torus?
No, it's considered a tokamak. Now there are also, in a spherical torus, there's actually a blending going on. And the reason is you have a very shaped plasma, which actually helps you in confinement, but there is a significant plasma current running through it. So a little bit of history. TFTR was built starting in the 1980s. It had a circular cross section. It had very, very large magnets in the toroidal field, basically going through the center and going around like this. They make a magnetic field that goes in and out. And it sucked up a lot of energy to confine the plasma. And people said, why don't we, we made 10 million watts. Why don't we just scale it up and make a power plant? And the reason is, sure, you could scale it up. You could spend a lot of money. You could build a power plant, and nobody would buy one bit of the electricity. Because if you're going to make an alternative energy component, it has to be economical. It has to compete with the energy sources you already have. So if you're buying electricity from coal-fired power plants at 11 cents per kilowatt, and then you build this big behemoth that costs billions of dollars, and now it's tens of dollars to get a watt of power out of it, nobody will buy it. You can't make it a commercial success in any stretch. So when NSTX came along, it had this shaped plasma. And this shaped plasma did a very, very cool thing. In TFTR, there was this number that said the plasma pressure pushing out could only be 4% at a maximum of the magnetic field holding. This is a parameter called beta. Now what that means was, for a given plasma condition, you had to have monstrous magnetic fields. TFTR was one of the largest power users in the state of New Jersey, with electric bills $750,000 a month. Okay? I'm not kidding. So the idea was, and again, nobody would pay to scale this thing up because it wouldn't be practical. NSTX, with its shaped plasma, even though it has a kind of a tokamak, it does that shaped plasma, and it makes a much more complex magnetic field. So these particles are, instead of just spiraling around in a circle, they're now spiraling around through a much more complex magnetic field configuration. That magnetic field configuration actually helps to confine those particles. So we think of, and NSTX, the shaped plasma, has a beta somewhere about 40%, which means for a given plasma condition, you need much, much less magnetic field and magnetic field infrastructure to build it. So we think of this as TFTR's younger, smarter brother. And I think we've demonstrated 27% of beta at this point, and theoretically it should go to 40, which means in the upgrade, we're hoping to we're going to be setting some world records with that, with the upgrade.
So that's 10 times better than the TFTR.
Yes.
Who came up with the idea of the spherical torus?
You saw two of them today. Masa Ono, who is now the project manager for NSTX, and Martin Peng, who you saw. Those two guys were collaborators, and they actually came up with some of the original work for this machine.
Interesting.
And what exactly is the role of the center stack?
So the center stack actually, in this case, plays two roles. One of them is it's a return path for the toroidal field coil. So you're driving current like this.
In a tokamak, there is sort of a core. Is it?
Yes.
Is it doing anything actively that?
Yes. That core, one part of that core is to carry that toroidal field current around.
That was always the case with tokamaks?
Yes, in tokamaks and even in spherical torus. The other feature that it has is there's something called the ohmic heating coil. Now, remember he talked about heating that plasma up? Well, there's a coil in here that we drive to 24,000 amps, and then we turn it around, and then we drive it to zero as fast as we can, and then we drive it to minus 24,000 amps as fast as we can. And that big swing makes a very changing magnetic field, which drives the mega amp to mega amp and a half through the plasma. We're actually going to increase that. We're doubling that to 2 mega amp plasmas. So the coil has to be bigger, take more heat, and last for much more seconds, if you will.
Is that the actual scale the man was there? Or is
Yes. Yeah. So
That's
you
much
can see.
smaller.
You can see how much smaller this machine is than like an eater machine, even the TFTR. It's about, in terms of the volume, this machine has a volume about 23 cubic meters, and TFTR had 90 cubic meters in terms of its internal volume.
How long
What
does
about
the
heater?
current
That's what I was
plasma
thinking, I'm not
burn
sure.
last?
In this case, we are usually limited by the thermal inertia of the machine. And you talked about the energy. What we do is we hit this thing with a pulse of energy to make up the magnetic fields, that we make the plasma, we heat up the plasma, and then very, very quickly we diagnose it and then we turn it off. And the reason is these coils are all air-cooled, or water-cooled, excuse me. And we're only designing them to operate so they go from about 17 degrees Celsius, and they'll go to 100 degrees Celsius in a second and a half. And the idea is now you've got to wait 15 minutes for it to cool down. Why do you do that? Because it's cheaper. If you had to have a continuously cooled system, that you'd have to have a much, much bigger water system to do that, much more infrastructure to power all that stuff. We use pulses because it meets the experimental requirements and it's cheap to do.
But how long could you hold the plasma?
In this case, from a second to a second and a half. In the upgrade, it's going to, they took it down. It's going to 2 to 5 seconds in some scenarios. The idea is we're going to extend that plasma out to get more confinement time to see how confinement changes over long periods of time and to do more things. So we're going to go down to the control room, but I want to show you a couple of things. So this is NSTX test cell right now. This is an older picture. There are 3 ways that we heat this plasma to 100 million degrees centigrade. The first one is that ohmic heating thing, where you're actually talking about the plasma being a single-turn secondary of a transformer. All right? You're just basically driving it, and you're driving current through that secondary of the transformer. Another way you do this is we take neutral beams, and we fire a neutral beam. And what's a neutral beam? A neutral beam is we take isotopes of hydrogen, deuterium or tritium, we ionize them, we strip the electron off, and then we accelerate that ion to 80,000 electron volts. And now it's an ion, which means it's affected by magnetic fields. And so then we take this very fast-moving ion and we put it through a very diffuse gas. And the electron transfer process to the ion is actually quite good and quite effective. So now you've got a good portion of these ions that are not ions anymore, they're fast-moving atoms. And because they're atoms, they're not affected by the magnetic field. And so they can come through the magnetic field bottle without being perturbed and literally transfer their energy by collision to the plasma components. And they can actually react with themselves, so you can have beam-beam interactions. So you have these fast-moving particles literally smashing into one another.
Into the plasma?
Into the plasma, yep, in the plasma, yes.
Which heats it up.
Which heats it up. It's actually very effective. It not only heats it up, giving you an energy density in the middle, but it also gives you a mass density in the middle as well, keeping the edges thinner, less dense. The third way we heat this up is with microwaves. This is ion cyclotron resonant frequency heating. We basically shoot radio waves into the plasma, and we couple them at various frequencies to the ionic components, trying to drive current in those ionic components. This is a very active area of research, and the reason is it has such tremendous promise for actually solving some of the Magneto hydrodynamic instability problems. Because the idea is you could basically, you can imagine taking this RF energy and powering or dialing it in to deposit somewhere in the plasma. And if you had instabilities arising in the plasma, you can actually localize them and then put some energy there and say, heal it up.
Kind of like adaptive optics
Like,
and telescopes.
like adaptive optics.
Uh-huh.
Not quite that way, but the idea is you could heal up the plasma. And so you could battle, if you will, these magneto hydrodynamic instabilities.
Sort of a way of tuning it almost.
Almost a way of tuning it, yep. So we're going to go this way. This was the TFDR control room. I have to assure the safety and that the machine is ready for operation and that the facility is ready for operation. So we basically clear the test cell, lock the doors, and we set a loop, which basically says if the doors get open for any reason, the machine will collapse. Basically, all those hazardous energy sources will be shut off and disappear. It's like a house of cards. I literally have to build the house of cards to get the machine to operate. And if the house of cards doesn't have good support, it'll collapse and everything will go to a safe condition. Anyway, so my day would start, I'd come in at 7 o'clock and I would start a motor generator set, which is basically big ballast. The utility does not like pulse power coming off of its transmission lines. We get our power at 138 kV from the tie line between South Brunswick and Trenton, which is pumping power to that black hole called New York. All the power in the Northeast goes to New York. Anyway, so I start the water systems, I start the motor generator sets, and then these guys finish up their walkarounds and lock the test cell in the column. At that point, I can arm and enable. Guys test the coils. The analogy I use is I'm the assistant conductor in an orchestra. Right? I get to warm the orchestra up. I even get to take some test shots. I get to play a couple of tunes. I can push the button, make sure all the magnetic fields are working, and then they all work correctly. And then I turn to the principal conductor, who is what we call a physicist in charge. He's the guy that's going to make the music. He's basically going to tell the machine when to turn on the different auxiliary heating systems, how much gas, when to put the gas in, what density is he looking for, what's the shape of the plasma he's looking for, the movement of the plasma. Did you grab that door, Arturo? Yeah, thanks. So he's the principal conductor. There's one other person in the room who's very, very important, and that is the composer. And that is the session leader, who's also in the room. Now, the session leader can be a man, a woman, a graduate student, could be from America, Europe, Japan, China, just about anywhere. This composer has written an experimental plan that they hand to the experimental team and says, this is important. And they look at it and say, yes, it is. We're going to give you time on the machine to run this experiment. So he takes his score, and he gives it to this guy, and it's this guy's job to turn that idea into an experiment that can be measurable and put out the data that he needs to write his paper. And from writing that paper, he goes to a peer-reviewed journal, and that's what our product is. Research in peer-reviewed journals. That's what we make. That's what you as taxpayers pay for. And while we're taking these shots, which are going off every 10 to 15 minutes on NSDX, please these pictures come up. This is a cartoon of the upgrade, but these pictures come up. These are actually films at 10,000 frames a second of the plasma. The green color is caused by lithium. Now you notice I pointed out over here about the people who run the machine. Everybody else in the room is a critic. They are diagnosticians. They look at this plasma in all kinds of wavelengths. They're looking at infrared, ultraviolet, visible light, soft X-rays, hard X-rays, gamma rays. They shine microwaves in, and we look at the reflections coming back. We shine lasers in, and we look at the reflections coming back, and they tell us things about the plasma. In fact, this is the big thing that Princeton is known for, is the diagnostics of high-temperature plasmas. Anyway, so they're taking that data. They will give it to the session leader. They'll be co-authors on the paper. But the point is, they give that data to the guy so he's made a prediction based upon what he thinks. Now he has the data to either say, yes, it worked, or, oh darn, it didn't work the way I thought. So we sit here, we run from about, the first shot is usually somewhere around 8:30 in the morning, and then we run till 5 o'clock shoot. We get off around 45 to 50 shots in a day.
But this is not operating today.
Not operating today because we're in the construction project, and we'll show you that in just a second. Okay?
The graph on the lower left,
Yes?
what is that?
That's actually an instability graph. It changes color. I don't know exactly its details, but I know they look at it and they're looking for changes in the color for instabilities.
And this is all within that second.
It's all within that 1 second. We're looking at this thing on, microsecond scales in many cases. Now the pictures, the videos, we have a 10,000 frame a second camera that's actually looking at this thing, and we can put different filters in it, so we can look at it in lithium light, hydrogen light, deuterium light, depending on what it is we want to add. We'll be starting up in September. The start date is September of 2014. So this is where we're clearing the platform, a lot more diagnostics. You can see that the vacuum vessel, the pumping duct is no longer connected, and there's actually a hole there so people can climb inside. And
It looks so light. You were describing you don't need the same.
well, inside there, what they do is they have a laser that actually measures the position of monuments in 3 dimensions. So we figure out how the machine moves. They turn that laser on, so when they take the picture, the inside of that's a little bit illuminated and looks cool in blue light.
But I mean, the structure seems much lighter than.
Oh yeah, these beam boxes are 50 cubic meters. This is 23, and I'm going to put another one over here.
That whole thing is just the little.
This big box, this stainless steel box, it actually sticks out here. It's a beam box. It's 50 cubic meters. Those things were delivered by truck from California. The one we're putting on, the next one we're putting on, that box hit a bridge somewhere between here and there. It took 2 years to repair the bridge, and the box was delivered without damage. Because it's so well reinforced because of the
Probably needed to be replaced.
So here's the next one. The platform's being cleared. All the RF piping has been removed. Again, you get a clear picture of looking inside. You'll see some of the ports are now actually being modified to hook up the beam box to it. The platform is gone. This platform, the 109-foot platform here, is now gone. They're now pumping, putting fresh air into the vessel, which means people are working inside the vessel on the plasma-facing complex. This is the beam box being flown in. So this beam box came out of the TFTR test cell. It gets moved out and it gets lifted by the crane, and it will be lowered into place. So there it is, all lowered into place, and you can see how tight it's getting. So this is the old beam box, this is the new one going in here, and this one's gonna end up looking like that. That's just looking down on it. It could be, there's a couple more, I'm sure. So we put the beam box in, and now they're building another platform, a higher level platform on this way, because all of the room we took up over there, we still have to put things back. So we moved them over to this, built another higher platform, and we put them over there.
Now, the beam box again is for heating,
Yes,
and that's where you put the
a neutral beam, yep.
neutral beam, but through a gas.
We basically take hydrogen, or deuterium or tritium, we ionize it, we accelerate the ion, we put it through that diffuse gas so it becomes a neutral atom. We bend the unneutralized things out of the way, and then we shoot the neutral atoms right through the magnetic field, and they impact the plasma and transfer energy by collision.
You couldn't accelerate it if it were neutral. So you
Exactly.
ionize it, accelerate it, and then
You
neutralize it.
re-neutralize it, yep. So you can see a couple of things here. These are where these are the toroidal field coils, these red ones. We've removed a few, they need to be modified. And these are where the toroidal field coils get connected to the center stack. In this picture, I believe the center stack is removed. We just pulled it out. It's disconnectable so you can pull it out. Why? The center stack is the most technologically challenging of the pieces on NSTX. All of the major risk of this machine is in that center stack. We've blown up 2 of them.
Wow.
So, actually they wore out. So they're basically wedges of copper with insulation between them. And the insulation breaks down over time. And when you're pushing 50,000 amps for a second, that's a lot of energy getting pushed through there. And when it finally shorts, it shorts big time. I know, I was in control of what happened.
Plug it into one of those surge suppressors.
Anyway, I believe this is the last view graph. This is what it looks like right now. You'll see what they call the swing set in position. That's for the neutral beam calorimeter. When the neutral beam is not firing into the machine, it's firing into a calorimeter, so we can keep it warmed up and measure its power, how much power it's actually depositing. So this is what the test cell looked like this morning. Every day they take a picture, and at the 8 o'clock meeting that happens here every morning, that picture gets distributed so people can actually see how the test cell looks. Since 2011. 2014. In the fall of 2014. Sure, why not? It's left here on the table.
So right now there's a picture of every day stored somewhere?
Somewhere, yeah. Somewhere there is.
You can do a little animation.
Oh,
Talk to
yeah.
Eric. If you want to do that, go see Eric Perry. He's the guy that takes the pictures. Anyway. Anyway, well, I've got one other thing we can do we can do the,
And where is it? Is it, and
Where
the
is what?
NSTX is?
So yes, you'll notice there's a loop road that goes around the laboratory, and inside the loop road and just outside of it, we call C-site. This is where the most of the action happens. Most of the people live over here. There is an area that's fenced in over just outside the loop, which we call D-site. All the high hazard activities happen within a fenced-in area. This is the legacy. It was built for the TFTR era, and we've decided to keep the controls that are necessary so that we can operate high hazard facilities in that area. And it basically has the fence around it because we were dealing with radioactive material, and that we had to make measurements to make sure the people standing at the fence didn't receive, radiation doses more than 1 millirem in a year. That's very, very small. The typical, you're walking around in the sun, you get about 360 millirem in a year, just doing your normal living. radon in the ground and standing out in the sunshine.
Especially if you eat a lot of bananas.
And if you eat a lot of bananas.
Bananas
They concentrate radioactive potassium.
Potassium good for you?
Yes. Anyway, so we had, when we were running TFTR, we had to prove that if you were standing at the fence line 24/7, 365 days a year, that you did not receive one extra day of dose in that 365 days. We had to prove that. And that was a very difficult project. So, let me see if I can get this. Oh, I'm going to show you a little thing. So, this is very interesting. What's going on here? In the old days, one of the things we have to do is we have to calibrate neutron detectors. And basically, neutron detectors, the way you do that is you get a radioactive isotope that puts out lots of neutrons, and you basically follow very careful protocols, putting it inside a pig, remotely removing it from the pig, and then putting it in position and keeping everybody out of the test cell for days to weeks at a time, and you move it around to different locations so you can calibrate the neutron detectors that are all around the machine. So one of the technicians said,
putting it in a pig?
yeah, it's basically a shield. You put the radioactive material in a shield, you carry it where you want, and then you walk far away and you open it and use it, and then put it back, and then you can move it again. Anyway, one of our technicians said, why are you doing that? Why don't you just build a railroad track inside the machine, and riding on that railroad track is a high energy nuclear source, and literally it's going in circles, and you want to be able to calibrate all of the neutron detectors at the same time. That's why this, and people think it's funny, but it's actually a very clever idea. And it just sits there and runs around. Slide, Vincent.
I don't understand, what does calibrate mean? Means measure or?
Calibrate means I've got a known energy source that's going around, right? And the idea is, if I have a known energy source and I have a known distance, there should be a certain amount of counts of neutrons hitting my detector. And that number will change depending on how far away it is and what the angle is off my detector. And the idea is I have to know what those numbers are for a calibrated number, such that when I see an experimental number, I'll know if it's more or less than where I am with my, is it a real signal or not?
So this is in the middle of the machine where
Yeah,
the plasma would be.
here's the center stack right here,
Yeah.
like that.
Now, where are the detectors?
They're actually outside the machine. They're in the hall, actually.
Is it the case that depending on the position of the train, the
Right.
that your figures would be differently because of the difference in the angles?
It's the difference of the angles and where they are around the
So,
the
right,
detectors.
so you have different readings for all these, and what
Yep.
you're looking for is divergence from all those different readings.
Exactly.
So if you have, and that by having this consistent
Yep.
track, it's right.
It- You make sure all the detectors are reading the same thing, and you can dial them in. Anyway, that's just something clever. I'm not going to show you the flyover of the machine. I think we've shown enough slides and so forth. Does anybody have any questions? We're going to take a little bit of a walk. Okay? I think we're-
Holy cow.
Come on in, come on in. Be friendly.
Oh, is that the center?
So, if you look on this wall behind you, that is a drawing to scale of the new NSTX center stack. Anyway, that, if you'll see a bunch of things, you'll see the orange things going up and down. Those are the TF conductors. You can imagine they're basically wedges of a pie that go all the way around, and they're insulated from one another. You'll also see like circles with dots in them. Those are the various control coils and ohmic heating coils for driving the current in the plasma. This thing goes inside of that thing, which is usually an Inconel shield. Basically, this thing is to keep the heat off of that. And these are all water cooled. You'll see the water connections at the bottom, the copper at the bottom, and at the top. There's also a cool thing. You'll see those U-shaped things on the top. Those are actually flexible connections. You can imagine a block of copper with electrode discharge machine, little grooves in it. So there are a lot of little, there are little flat plates that, and you can actually do this and bend it. Where is that? Yeah, we had a. Yep. There's a little mock-up just back there behind the welding shield. You can see it.
For the thermal expansion of the copper during the...
This machine grows by inches when it's operating. So you need to be able to take that movement somewhere. Otherwise you just break things apart. And that's where we figured we need to push the center stack changes a lot more than the coils on the outside.
Right.
So you have to. So what were they doing here? This. Oh, we can go this way. They took all our posters down for NCSX. Anyway, I think I can explain this. So this piece of hardware right here is one of the pieces that we are keeping here from NCSX. What is NCSX? Princeton proposed a project called the National Complex Stellarator Experiment. It was a shaped stellarator, i.e. the plasma had a shape to it, and it had a threefold symmetry, so that shape literally rotated around in space 3 times before it came back on itself. It was a stellarator, which means all the magnetic transform had to come from the outside. To actually do that, you needed actually a very complex coil system. 10 years ago, you couldn't even do this because there wasn't the computational models to do that work. But with advances in modeling and computer technology, we're able to actually do not only equilibrium calculations, but sensitivity calculations. And so we were able to pick a series of coil shapes, magnetic coil shapes, that would give you the magnetic transform that you wanted to give you that shape and holding power of the plasma. What this is a this is one without the vacuum vessel. This is a near net-shaped casting, and you'll see the copper sections are actually wound coils on that near net-shaped casting. This casting is made in a mold, and then it's put on a 6 degrees of freedom milling machine. And it literally is milled to the right shape. Using similar technology, you can actually take a measuring device and go in with that arm and touch it to various places, and you made this cloud of data points. And now you can take that cloud of data points in your computer, and you can overlay that onto a CAD model, a perfect CAD model of the coil as you've made it. And you can tell whether this place needs a little bit more, this one needs to be ground off a little bit. The idea is to get the magnetic center within millimeters of where you proposed. So these coils are actually, they've been wound, and then they've been epoxy impregnated. Inside of there, you'll see this vacuum vessel, which kind of looks like it twists around. It's like that is made of Inconel. It's actually a shaped, twisted vacuum vessel, and the way you have to put it on is you literally have to screw it on. And so the two sections, the sections get bolted together, and then the vacuum vessel gets screwed on. So what happened? Why are these things here? So, like all good projects, we estimated what it would cost to build this machine, and then we started building the machine, and it turned out to be a lot more difficult than we thought. And so we went back to the Department of Energy and said, okay, we're not going to get there with the construction budget we have. What do you want to do? And they said, shut it down. So we've got about $40 million worth of hardware in here waiting assembly money. It's
How
literally.
much would that be?
We expect it to be about 40 to 50 million, basically about double. These coils would also be cooled by cryogenically cooled. We would literally use liquid nitrogen to cool them down to like 77 degrees Kelvin, and then run them from 77 degrees Kelvin up to 100 degrees, or 475 or whatever. So you get a much bigger swing.
Does the, do any of these use superconducting magnets?
No, they do not.
Okay.
And the reason for that is that that's a whole other level of complexity and cost to go into that regime.
Remember years ago, I read about room temperature superconductors. That
Yes.
were supposedly coming online. Is that affected?
They're not actually room temperature. The most effective ones are actually capable of being liquid nitrogen temperatures. Now that's a very good thing because liquid nitrogen is a byproduct. It's actually cheaper than beer. It's like 28 cents a liter or something like that.
You got any?
About 77 degrees Kelvin it liquefies, but you can run it a little warmer than that if you pressurize it. So 80 degrees Kelvin is a good number.
So that's about state of the art for so-called room temperature of semiconductors.
Yep, I'm sorry to say. And the reason is they lose performance inside of a magnetic field and through high current densities. But you want high current densities in order to reduce the amount of material you have to pay for. So that trade-off isn't really economical yet. Now there are superconducting applications around the states right now. One of them is in Chicago. They have a superconducting line by, I forget the power company, but it goes under part of the city and comes up into a substation.
Really?
Yeah, you can actually see that installation.
In like the municipal
In the
power
utility
system?
power that goes into Chicago, yes.
Really?
Yeah.
The idea there, the superconducting means that you have a smaller cross-section of material that can carry a much larger amount of current?
That's correct. And but you have to build, you have to build a cryogenic compressor plant. You have to have specially designed jackets for this so you can pump the superconducting down, and you have to make sure that the temperature doesn't change along the entire length. Because if it goes normal somewhere in that line, you've got to detect it and shut it down almost immediately, otherwise the cable will melt.
Amazing that would be considered commercially viable.
It was because they couldn't get a right of way to build another tunnel to bring another cable in, so they had to use an existing one.
What did you say the name of this was again?
This is NSTX, the National Spherical Torus
No,
Experiment.
the thing that wasn't built, is this, did you say there was a different name?
Oh, NC?
Oh, this is NCSX,
Oh.
the National Compact Stellarator Experiment.
Just so I'm clear, so this would be one, these two would come together?
Yes, the idea was to build these sets of coils in sections of 3. And the idea was now we would have 4 sets of 3, and you literally bring them all together and bolt them all up.
And what's the shape of the?
It's like the shape of the chevron, so it's got a little point, and it comes out, and then there's like a cave back, or an AND gate, if you know what that looks like, the schematic for an AND gate. And you can imagine that shape just being rotated 3 times and then back onto itself when it comes back.
And looking here, is that the inside of what would be the plasma chamber?
Yes, that's inside of there.
And what did you say it's made of?
That's made of Inconel, a very high nickel alloy. 625, I think, I'm not sure. These are very, very expensive pieces of hardware, let me tell you.
Sure.
But
When were these
The
built?
machining is really
How old?
probably a year ago, a year and a half ago. So just a little tidbit. So Energy Secretary Chu has left the administration, and he sent out his missive explaining all the things that his tenure at the DOE had accomplished. It covered 4 pages in small type. And fusion is not mentioned in there once.
That's because they didn't achieve much of anything.
They didn't
Or
put
they
much money into
They
it.
didn't, yeah.
Didn't Obama say something about we don't need no fancy fusions?
Yeah.
just insulate your window.
Anyway, does anybody have any questions?
Well, now, the way that that's machined inside.
Yes.
Now, that's your, the sort of negative curvature thing going on, don't you?
Yes. Actually, the way the vacuum vessel is produced, the vacuum vessel is made up of 5 pieces that are stamped, and then they are put together and then welded together to make an entire vacuum vessel. The big deal there is you need to weld them in a specific order and in a specific fashion to reduce, what do you call it? Distortion from the welding. And the tolerances on these are sub-millimeter kind of tolerances.
Yeah.
I missed the very beginning. This is the National Compact
Stellarator experiment,
Stellarator
which was
experiment.
canceled by the Department of Energy.
Right.
But what was the goal? To demonstrate that you could do the same thing?
Basically, the next step in Stellarator research. The idea was,
Follow on to the NPSX?
well, basically, we're trying to run the parallel course.
Right.
What the Stellarator
experiment.
gives you is, because all the magnetic transforms from the outside, you can have a steady state plasma. And if you can build a steady state plasma, it means it's more, the plasma is more stable, and it's more, not economical, but it's more attractive for a power plant kind of design.
Maybe I'm misunderstanding something. The NPSX, is that a Stellarator?
You mean NSTX?
NSTX, I'm sorry.
It's actually a combination Stellarator, and spherical tokamak is actually an advanced kind of tokamak. It borrows some of these things about shaped plasmas from Stellarators, but it still uses a plasma current like a tokamak. So it's kind of a little of both. It's kind of a hybrid. Nope, this is pure Stellarator. No plasma current. No plasma current. Okay?
Yeah, but these are like additional experimental tracks that you wanted to run parallel with what you were doing, so that
Sure.
you actually could get an
It
idea
happens
how
that
to
our
do it.
director is from the University of Wisconsin, which, by the way, has a very large Stellarator program. So maybe they'll resurrect this at some point.
Wow.
Any more questions? Thank you. We're going to head back to the lobby, and we're done with the tour.
There's, I guess, a little bit of variation of like, in terms of the sequester and how much money we're gonna get for that might vary. But right now, the plan is June 1st, we're gonna open house, we're gonna open the NSTX cell, we're gonna have a tour, it's gonna be pretty good. So, everybody's welcome.
So that we could see.
Yes, the test cell will be open for that day.
But you also want to have the people from the neighboring towns.
We want the people with bring your children. We will have activities for children.
We're gonna try to get, scientists, politicians, community, people from all over the country, maybe even the world, to come here. We'll open it up for a day. We'll have activities, children.
Could Diane set up a table?
Be here, she can bring her.
Two questions. Back in 1980, when Representative McCormick got the bill passed to make fusion a national priority,
Yes.
he talked at that time about how there should be a commercial reactor by 2000, 20 years.
Okay?
If fusion were made a national priority today,
Yes.
whatever that means in terms of budget,
Right.
would you hazard any kind of estimate of when, well, I shouldn't say power producing reactor, because you do produce power now.
Right.
But
So let me answer that by saying that I couldn't hazard a guess on how that would happen. But I can tell you that the laboratory does, actually not just the laboratory, but the fusion community in the United States every year goes through the exercise of making a 25-year plan. And they've been doing that for 40 years, making a 25-year plan, and basically laying out the priorities, laying out estimations of dollars and what the funding levels would need to be, and we do that year in and year out.
But let me put an analogy. Right now, South Korea has been putting a lot of effort into the fusion program, and they have built K-STAR, which is a very big fusion device that is already in operation and that's already getting a lot of interesting data out. And now with collaborations with PPPL, actually, they are in the process of designing and building demo, which is called K-Demo, which is going to be effectively the next step after ITER. And it would be a plant that has a test blanket so that you could actually get power from the neutrons coming out and everything. And they're designing and building this because there's a lot of support for this research over there.
Yeah.
Now, of course, the science has to be developed and all that. And as we said, 20 years ago, a lot of the what we know now about the physics of plasmas we did not know. And things as science goes, you would have to make an experiment, see what you learn, make another experiment, see what you learn, and all this. But a lot of these things could have been done in parallel. Like we could have been building Stellarators. Maybe we would have learned something from an earlier Stellarator that we could have built upon in the next one and all of this, right? But it was always the fusion program has always been starved for money. We've always been constrained. We've always been constrained about what we can actually build. How much money is going into these efforts.
When the NSTX would be working back in its operational phase,
Yes.
you'd be doing experiments 5 days a week.
5 days a week,
Yeah.
usually for 3 weeks on and 1 week off. Generally, the 1 week off is so that the diagnosticians can go out and tweak things and recalibrate things, reset things up. It also gives them time. You're going to laugh, but it's actually very true. Sometimes these machines are so productive in terms of data, you have to stop so that they can look at the data that they've got to tell whether they need to do something different. I think this is my personal opinion, one of the big advantages, I guess, of an STX versus the other machines in other parts of the world is that we can change direction much more quickly. In places like Japan and South Korea, and even in China, they have much more rigorous, you must follow the plan kind of thing. And here, it's a little bit more, I don't want to use the word wild, wild west, but it's a little bit more, hey, this is really cool. This is new physics.
Yeah.
Let's change the direction of the boat and go this way and see what that tells us. And in fact, some very big results come out of that kind of thing, where we're able to turn and come up with a new idea. We talked about lithium walls. Why? So, you can look at the machines we're currently proposing, ITER being one. And if you look at them, the plasma-facing components, the first ones are solids. If you were to build a reactor, there is no known solid material known to man that would survive in that environment. So the idea is, how about we make it liquid? So you had liquid lithium literally flowing along the surface. You could actually use it to absorb the neutrons, get heated up, pump it away, cool it, either through producing energy, and then put it back in and do it again. You don't have to worry about it melting because it's already melting. And there are a lot of problems with doing it. This is Adam Combe, our deputy director.
I was hoping to be anonymous.
Sorry, Adam.
You did a very good job.
I wanted to listen.
You should introduce yourself.
Hi, Diane, Sare. I'm running for governor.
Oh, good luck.
Thanks.
We need your support.
Yes, you would have my support.
All good. Jobs for New Jersey. Good
Yes, exactly.
energy source for all the future. If you ever have any questions about nuclear or whatever, this panel is the New Jersey Department of Environmental Protection panel.
Yeah,
I'm
I
the
testified
independent
at the
member.
Energy Master Plan hearings.
Okay.
I proposed, well, I won't say what I said at the meeting. I said it, actually, I said they should develop a nuclear fusion rocket which could propel Obama and Christie to a different galaxy. But,
We are actually working on a fusion rocket.
Well,
Are you?
We're not, but there's a company that's licensed the technology from this lab because they think this is a key way to develop a rocket to go to Mars and back.
yes,
So it's a little science future, but it's based on science fact.
right. Do you recall the Fusion Energy
laboratories
Foundation?
probably 95% funded by the Department of Energy.
Because
They own all the
you may
buildings.
or may
I'm
not.
relatively useless to the fusion field. I've only been here 4 years, but my whole career is fission and nuclear power.
Okay. Anyway.
admit I'm actually a proponent, but I think it can be done safely. So.
We're total fanatic proponents. We needed it like crazy. No, Lyndon Bush founded the Fusion Energy Foundation years ago, and then he came into a very raucous dialogue with Edward Teller. And yeah, and that was the genesis of the Strategic Defense Initiative of Reagan. And we're actually holding a conference on March 23rd on the 30th anniversary of Reagan's famous speech announcing this, and we're bringing in a lot of the scientists and military people involved in that. So I'll give you a flyer next time we know people or whatever. Yeah.
Franklin Hippel, was he going to use this at the university?
Oh.
Because I'm pretty sure he was involved in that.
Was he? Oh, great. We should get him.
I mean, he was probably the one who was saying it was crazy.
Right.
What did you say? Franklin Hippel from the university. He's a professor at the Woodrow Wilson School, and he's the one that always gets trotted out for discussions, scientific-based discussions on the value or the lack thereof of reprocessing fuel. So sometimes we sit on the opposite sides of the argument, but it's fine. I mean, it's a good, healthy argument.
Well, are we going to get these next level reactors, like the breeder reactors of these small modular, high temperature?
So the small modular, yes. I actually think that's a good idea. I don't think it's as good as the hype is portraying it to me, or at least I have to be convinced of it.
Right.
Rickover has a very famous quote where he said, paper reactors are always clean and cheap and they run better, but real reactors are dirty and they're expensive.
Right.
So the idea is, this is a paper reactor, and on paper it looks great. I mean, you can build this in a factory and you can ship it, and it sounds wonderful.
Right.
I think it's a compelling argument, but I want to see this actually work. I mean, for example, it's great to talk about something being built in a factory, but how many do you have to build before the factory all of a sudden becomes economical to run? It's obviously not one, but is it 10? Is it 100? And then let's start talking about what's the arguments pro and con. I think it's reasonable to expect that this country could build large-scale reactors, but they need to be done safely, and the latest technologies allow them to be run much safer than the past technologies. The question is, how do we retire the existing reactor fleet in a reasonable way so we can get the benefits?
That it is necessary to shut down oyster creek? Because they're trying by what, 20 years? Yeah. Is that really necessary?
I think it's a good step because the cooling towers really would be better to run, and now it's an economic decision. Do you want to put up the cooling towers and run for 20 years or 20, so 16 more years, or do you want to kind of fish and cut bait? It's an older reactor, it's inefficient, the size is 660 megawatts, so it's about maybe 50% of what a current scale reactor would give. So I think everybody recognizes economically it probably does have a specific lifetime, but it's not that it's unsafe, it's running very safely, it's just it's economics, it's not the best return on investment.
But we have to bring something online. I mean, we're not going to replace this with solar panels and windows.
No. But there could be something that is built. I mean, I know PSE&G was looking at something down in the other plot.
Another nuclear fission plant.
Fission plant, yeah. And then there are other sites in the area that could easily wheel power in the mid-Atlantic compact into this area. So it doesn't have to be in that area. It doesn't have to be at Oyster Creek. My belief is it could be, and it's reasonable to expect we could design a plant that runs safely. But I also understand there's a lot of people who want to see Barnegat Bay saved at any cost, and I agree with that. I think we should preserve these resources. So it's an interesting panel. I mean, the panel, the whole idea is to make sure that whatever steps need to be taken between now and 2019 when it finally shuts down, but certainly before then, that there's a decommissioning plan, that the path forward is laid out, that we know what decisions are being made by Exelon and by the NRC. I mean, it's a state panel, so it's got the power of whatever the state can do. Usually that means like a letter or a phone call from the governor, but that's about it. But it's reasonable to protect the folks' interests, to make sure that path forward and plans for decommissioning consistent with the 2019 agreement are being taken.
Right. But how long would it take to get a new nuclear plant online?
Somewhere between 5 years and forever, depending on.
Well, that's the problem, because I mean, if we take this plant down and we don't immediately start on something else, then we're going to have.
Yeah, we need to be building nuclear plants in this country. We don't have to have wild exuberance to build them to excess. I mean, we don't have to exceed our current needs with capacity, but we need to meet our current needs with capacity. capacity.
Right.
And we know what the projected expansion of electricity demand is, at least in the 10-year
Well, the
horizon.
projections are probably insanely low, because like Ray was saying, if you actually wanted to have an economy committed to, say, the development of fusion, then there's all kinds of new infrastructure you'd have to build.
Yeah, I mean, fusion plants actually can plug into the existing grid, because they will generate power pretty much the same way. You'd have a central location, you'd have large-scale power put on the grid and distribute it out. I mean, one of the things that we want to see is really push forward on fusion, and let's make a decision in the 10-year horizon, the 15-year horizon, as to whether we have something on the books that we can really do or not. You know, and we can continue to do research, and we need to understand the scientific basis for fusion, but we could move much quicker than the government funding right now is allowing. Much quicker. The ideas are there. It's not that we're doing R&D to develop ideas. We know the next facilities that need to be built. We have ideas as to how to solve some of the issues. Materials is one issue. How you breed tritium, because you need tritium as fuel. We have ideas about that, but we need the facilities to test them, and that takes funding, and funding is not prevalent right now.
Yes, yes.
So anything you can do to get those messages out, but you know, labs like this really, they're one lab for the country. This lab happens to be focused on fusion energy and studying plasma physics. The reason the government funds these is because it's expensive. If it wasn't expensive and it was easy, companies would be doing this. But it's expensive, and you group the experts together and you develop facilities that the world can come and use and see and use the research results. And that's why we're here. So it's sort of a shame that we're not using labs like this to full capacity. Keep pushing.
Good.
Other questions?
Yeah, I wanted to ask you, said there was some company who's licensing some of the technology from here for a fusion rocket.
I don't remember the name, but I know it's a company that was interested. Princeton Satellite Systems, maybe. It's a local company. It's a small business, but the idea is, can we use the technology that's been developed for generating fusion energy to some other application? And he has thoughts about how you can use the energy source and use that as a propulsion source as well. You know, plasma thrusters are actually a real source now. Oh yeah, it's used for rockets and certainly satellites. But the idea would be, for a fusion reactor, you have a very small amount of fuel loading, and reasonably you could reduce the weight of the rocket, and then you get much faster, much further with a fusion type rocket. So that's his idea.
Let me ask a wild idea. If we, because you know, I mean, the sizes of the fusion plants here being built on Earth, you know, they're a certain size. If you were going to build something enormous, like if we totally geared up for this, we're going to go to Mars, we're going to use a fusion rocket to get there, and the scale is, you know, beyond ITER. Let's say we're looking at like the terawatt range in terms of like an actual power capacity. My question is, does the scale resolve, how much does scaling things up like that, you think, would resolve any of the problems that are currently making it hard to achieve?
That's such a good question. I mean, obviously bigger on Earth makes it easier to maintain, and you can, instead of having a large heat flux on a small area, if you spread out the area, you can have a smaller heat flux, and maybe it's manageable. So scale does help if you're going to have a power plant on Earth. Generally, rockets try to get a smaller scale and compact as possible. The ITER is a tokamak. The fusion rocket, I believe, is based on a field reverse configuration, which is another type of fusion reactor that would rely on deuterium, helium-3 fuel, if I remember correctly. So it's a small effort here. It's not the main thrust of the work we do, but it's still a valid fusion concept. And the idea is that would scale up to something that could fit into a rocket, or into another tube, like a submarine reactor based on fusion would probably be based on something like that as opposed to a tokamak.
Yeah, because as an overall power source, that, I mean, if you think about what mankind's able to do with when we first introduced fossil fuels as opposed to a windmill or a water mill or something like that, totally changed what we're able to do.
Right.
And now in space, the last issue of the magazine I run was about planetary defense. What do we do when asteroids are coming? And people are saying, well, we could paint them. Now, look, there's studies that applying the paint to the asteroid will have more of an impact than the difference in the solar radiation hitting it. But I mean, really, if something's coming with a short lead time, as many of these are, since we're not doing that much of a job finding them, or also if it's a long period comet, The only way you're really going to be able to move it is if you've got a lot of power and energy you're able to apply to it.
That's probably true. I mean, it's not my field, but I can imagine that would be true. I don't know. I've heard one idea that they were talking about not necessarily painting it, but planting like reflectors on it. So you can imagine, having a satellite that just launches mirrors onto the thing.
I know. If you know about it 20 years in advance, sure. But if it's short term, that you need nuclear technologies either for an explosive to push out of change its trajectory or maybe blow it up, or to and to reach it quickly. And so that's one thing with fusion, because the weight of the fuel compared to the power you're going to get out of it is so phenomenal.
Yeah, it might. I mean, I guess if you could imagine planting a fusion reactor on this thing and then lighting it off so that it...
That's one of the things they talk about, them landing on it with a rocket right now. Yeah, but
I would imagine the fusion rocket could be the delivery mechanism that you deliver a payload.
And you could get there very quickly with that. I mean, if you're able to, if you had enough of a power source where instead of just doing an initial burn and then waiting until you get close and then you're there, if you're actually firing constantly, you could get to Mars within a week. If you're accelerating, yeah, and that's what I was wondering about it, because the size of rocket required for that, the amount of energy required, would be phenomenal. And so I was wondering. That's why I was asking if that scaling would make some of the problems that plague the smaller ones less of a problem, or
it might. I mean, I will remind you, I are an engineer.
Okay.
I'm not a physicist who's okay. I mean, but we have plenty of those on here. I mean, I actually try to solve problems that we can actually. But it's a reasonable expectation that the larger rocket would give you the thrust that you need. I mean, because there is still a thrust to weight ratio, and you're willing to sacrifice the weight, in other words, add more weight, and you have a lower amount of specific fuel capacity, then you could get more thrust out of the smaller amount of fuel with the larger rocket. I mean, that's reasonable.
Yeah. Okay. Do you know how much I was wondering this earlier, it said on the tour the ITER would be expected to have a payback ratio of 5, the energy out versus energy in. And I was wondering how much of that is, based on how it's designed differently versus just the fact that it's so much larger.
It's more to do with the latter. So the Q, I believe they're advertising, is a Q of 10. Okay. Q meaning that the amount of energy that you'll get out from the fusion reaction versus the amount that you put in from all the stuff you need to heat it, whether it's the beams or the RF or the current that you have in the magnets. That all takes energy. So the amount that's put in versus the amount you'll get out from the fusion reaction is essentially 10 times. I mean, 5 times is probably comfortable, but they advertise it as a Q of 10. And that's just the amount of fusion power that would come out. You'd still have to convert that to electricity, and so if you were in the Rankine cycle, you'd be in the 30% range, and you'd have a balanced plant where you'd have a steam cycle and the like. So maybe it's a 500 megawatt reactor would produce 130-ish, 150-ish megawatts of electricity out if you were designing a plant to do that. Does that answer your question?
Well, but you were saying the latter, that it's the part of the scale. I mean, the scaling being part of why that's the case with ITER.
Yeah. So what they did was they projected out as to what scale tokamak you would need, and how much of this heat versus fusion fuel or plasma that you would have producing the energy, and that's why they came up with a large scale in order to produce this Q. The whole idea is to get to this burning plasma regime, which would give you this Q of above 1, whatever it is.
Okay. That's sort of where I was wondering about if it was even larger, just like if you had a very large scale thing, if it makes it easier to get a better return.
My understanding is ITER design, they originally wanted it larger, and because of cost, they scaled it back to this size. But the power plant doesn't have to be as big as this. They think once they figure out how to make this steady state, how to resolve some of the issues with tokamak, how to make it run, how to inject the fuel, they think that this could be maybe, 80% for a real reactor. So you'd have a core that would be 80% of this. This is large, but it's not really that much larger than if you think about what a containment building is in a fission plant.
Right.
It's really not at a scale. I mean, It's big. It's not that much bigger.
Well, it's a lot bigger than, what you got here, for example.
Yes, yeah. And this is big. I mean, I actually serve on the review committee for ITER, it's the management committee.
Very nice to
You as well.
Thank you.
And
We'll be in
that's
touch.
well, yes.
Thank you.
But the management advisory committee, so I go to France every once in a while to see the progress of the construction, and it's wonderful to see. As an engineer, you see a big pit, and now you see the seismic loadings, and now you see the floor being passed, and the buildings are starting to rise. And it's exciting to see the project, but it is big. I mean, it's a deep pit, and it's a huge plateau. But you could build something like this in Oyster Creek, in that area, and you wouldn't notice it.
Yeah.
You could drive by in the Garden State Park, but you'd never see it. So while it's big, it's not that big.